right, this is the part 3 on global freshwater resources. So let's take a look at freshwater resource usage in the US. Um, Aside from the prominent things like household consumption, what else do we need water for? Yeah, of course, irrigation. Largely for farm fields, for crop farming as well as for animal farms. You need a lot of water. Um, and then to keep these municipalities going, other source of public water supplies, for many industrial needs, which includes cooling power plants. There's a multifaceted demands for fresh water. The US water supply, well, um, within the country, it's not bad. It's not a country that has historically suffered from water scarcity or used to have historical water related issues. If you look at the annual precipitation map, right, the entire eastern North America, kind of the entire part of the country somewhat east of the Mississippi River drainage basin, actually received very high level of precipitation, ranging between at least 81 centimeters per year or more. That's very abundant supply of water. And of course, the southeastern part, in and around the Mississippi River basin, the southern Mississippi River basin in the eastern United States is much heavier in terms of rainfall. Um, and then, of course, the westernmost part too, particularly along the western facing parts of the mountain ranges, still you get, ample supply of water. It is this intermontane part in the western US that actually has some sort of a water scarcity where you get rainfall less than 41 centimeters per year in terms of precipitation, right? And within that, I would say the southwesternmost part is actually the Colorado basin could be among the driest areas, right? And then again along the western US, we do have several deserts, the Oregon high desert, and within California, Nevada, Arizona, you get several deserts that are known to receive very little precipitation. So if you look at the drought index or the water stress index in the US, it's again the same area where we experienced natural reduction in precipitation, particularly the southwestern part, Southern California, to be in particular, um, are experiencing the high drought, high water stress conditions, and prevailing problem of climate change has increased this natural stress and kind of aggravated it. Um, and then if you look at the third map on the bottom left, right? So we do experience, we have some evidence for groundwater pollution. What the map shows nitrate ion concentrations and specifically surface water contamination of nitrates dating back to 2002, so more than 10 years back. And in that map, you do see that areas around Great Lakes area, as well as certain parts of the Great Plains, tend to have greater nitrate ion concentrations in the surface water bodies. Now, if you look at nitrate contamination in shallow groundwater condition, like kind of you see a much more dramatic picture where the areas that have intensive agricultural practices in operation, parts of, well, the Great Lakes area, the entire Great Plains area, right? With the greater the agricultural intensification, the greater the risk of groundwater contamination. Um, so now this groundwater contamination, is largely due to agricultural problems rather than industrial problems. In the previous image, when you looked at surface water contamination in the northern central US, now that can be attributed to historical industrial pollution, and it's really hard to get rid of that pollution. why actually that's one reason why I showed the an image from 2002 during when these contaminations were much more severe. No, this is exactly why this strict regulations regarding industrial pollution is required. It takes a long time to get rid of that level of surface pollution, but if you relax on those regulations, that problem again will reoccur, and then again might be harder to get rid of those contaminants, particularly in surface water pollution. Pollutants like nitrates can get bind or bonded to sediments, suspended or bottom sediments, and periodically resuspend back in the water column. So yeah, the bottom line that I wanted to reiterate is that um, there is an uneven distribution of water, right? There's a gradient of water stress. There is little stress in the eastern part, and it becomes a little bit more intense in the central part. And as you move towards the western, the water stress becomes intensified. The same thing regarding the precipitation gradient. In the eastern part, fairly well um, abundant supply of precipitation, but as you move towards the western part, you do see some unnatural decline in precipitation. And the drought issue is actually kind of an intensified situation. It is in the southwest where you get the extreme level of drought um, conditions, and as in the eastern part or in the northeastern part, you have less of that problem. But do not forget that now, within the current decade, even the Northeast is experiencing a reduction in overall average annual precipitation. But the conditions are much more dramatic in the Southwest, despite the fact that those areas have historically been adapted to low water supply. Existing drought conditions or aggravation of drought conditions in the North America Southwest is much more severe. So I did mention that the southwestern US in particular is drought susceptible and historically received less precipitation compared to rest of the country. Um, Now I also, want to talk about how severe and how worse this situation has become over the years. Um, so because of the increasing droughts and reduced precipitation that we have been experiencing in the southwestern US, in different parts of the western US, we are going to experience or anticipate um, different um, increased conflicts on water demand and supply. When I mean a conflict, I meant there's a higher demand but less supply coming through. So, the reds and oranges are more prevalent in the western part of the country. And then the Colorado Basin is particularly important to talk about this. In the map to the top left, you do see kind of the hydrology of the Colorado Basin. And Colorado Basin within the all US rivers has been the most modified river. Um, Particularly along the main stem, it has been impounded several times. Starting from 1950s, the river has been impounded so many times. And in the image, in the map, the if you look at the dams, you see one, two, three, four, five, six major dams right along the main stem. And because of this, since 1916, particularly along its lower basin from within Arizona, the river has dwindled from one of the largest, many meters wide river into a small sluggish stream or like a creek at the point when it reaches Gulf of California. Right at the moment, it actually flows through the lower part of the southernmost part of Arizona. I mean, it enters Baja California. It's nothing beyond a small sluggish river. Sometimes even that completely disappears. Um, Throughout its course, you don't see a continuous flow given the high degree of impoundments and water withdrawal from those impoundments. So Well, does climate change has anything to do with the droughts that we experience in the southwestern US in the Colorado Basin? Well, certainly, undoubtedly, there's a lot of data to support that. But more than that, well, not more than that, in addition to climate change, it's actually the impoundment that has been the greatest threat to reduced flow, reduced stream velocity in Colorado Basin. Look at the figure you are looking at. On the left axis, it's flow, billions of cubic meters. On x-axis, you are looking at years from 1910 to 2020 projection, right? Um, so the flow of Colorado River, particularly at its river mouth, has dropped sharply as a result of multiple dams. The total number of dams in the main stem and major tributaries is over 15 as of now. The water withdrawal is mostly for a variety of purposes, mainly for agriculture and then urban water supply, municipal water supply, and then of course the drought condition is also a problem. And in fact, in the graph now, you can see the first dam. The first major dam is the Hoover Dam that was completed in 1935. Look how much the water flow has declined since construction of the Hoover Dam, right? On average, from around 20 to 25 billion cubic meters. Now, after the construction of Hoover Dam, it has dropped somewhere between 5 to 10. Well, despite that dramatic reduction in the flow in Colorado River Basin, they subsequently constructed in about 30 years or more, in around 30 years, slightly less than 30 years, they constructed Glen Canyon Dam in 1963. And since then, you even observe like multi-year seasons where the flow in the river is remarkably low, and then of course after a storm it spikes up, and then again dramatically after the storm it goes down. So right now we actually observe, on average the river flow could in a particular year go below 5 billion cubic meters, and even approaching zero in certain cases, or like unremarkably low compared to what it used to sustain. Historical analysis. In order to understand the historical data or historical flow regimes, certain botanists have done tree ring analysis where they actually take a core of larger trees and try to see whether they have actually remarkably reduced tree ring growths in historically with respect to certain old growth trees. And the analysis reveals that at least once in every 100 years, the entire southwestern US, the Colorado Basin in particular, um, have suffered droughts, and each drought within that century may have lasted as much as 10 years. So even in the southwestern US, historically there have been mega droughts, but that happened very less frequently. Once in every 100 years, a 10-year long drought. But currently, we are actually seeing a major alteration of this lower drought frequency, right, in a naturally dry area. So this level of hydrologic modification, only makes things worse for dry and arid southwestern United States. So, in the Colorado Basin, as you construct so many dams, impoundments across the river basin, it actually slows the river flow, right? And that results in deposition of suspended silt, sediments, and soil particles on the riverbed, on the reservoir bed. Now, the silt and sediments are extremely important ingredients to maintain the coastal ecosystems, the delta ecosystems, the river mouths, and the bay system. In the Gulf of California, you actually get multiple types of brackish water wetlands, and you cannot maintain those habitats without deposition of silt and sediment. What would happen is actually the continuous movements of coastal waters, it could actually increase erosion. With the erosion, how you circumvent erosion or kind of compensate for erosion is by deposition of silt and sand and sediments. With the impoundments, it actually retains those suspended soil particles or particulated matter, and completely altering the wetland habitat in the river mouth in and around Gulf of Mexico, sorry, Gulf of California. Um, so that will result in declining diversity of coastal wetlands in Gulf of California and also at the river mouth of Colorado River. Um, and then what happens to the reservoirs as those soil particles, sediment deposits, that actually elevates the reservoir bed and effectively reduce the water holding capacity of reservoirs, and that reduces the reservoir's capacity to retain flood water or to retain storm water, um, and so it results in floods. Increases the flood frequency, right? And also, since now the effective volume of reservoirs have declined, those reservoirs can no longer produce hydroelectricity to the level they used to. So as a result, you actually have to create those blackouts in order to sustain the hydroelectricity production. It cannot sustain the growing demand for irrigation water or even for drinking water. So you have to impose these restrictions in water supply as a result. Um, so what you're seeing in the top image is actually what would the flow look like in a low flow condition. On the bottom is what now it looks like in Colorado River main stem um, during a low flow period, right? We are looking at only like less than one, maybe maybe even less than 1/10 of the entire river channel is now being occupied by flowing river. And sometimes what happens is, since the overall discharge is so low, um, the standing water areas in the river is also fragmented. It does not flow continuously, so it actually even alters the loading or the flowing water system within Colorado, and that changes the biota living in that water. And the problem here is when the U.S. Army Corps of Engineering, pioneered these kind of impoundments. The governments were not thinking about the ecological needs; they were only looking at human needs. So there was less insight or less thoughts have been given to the long-term consequences. And also with the reduced flow, what happens to the impact of pollution? The surface runoff will keep dumping pollutants into the river basin, into the main stem, into the tributaries, and there will be no dilution, right? The pollutants will concentrate, but there will be not enough water to dilute it, or enough water to flush it from the river basin into the ocean, into the wetland systems to recuperate the pollution, right? That will not happen. So the impact of pollution will aggravate over the years within the entire river basin. So there are two important terms that I want you to understand here: water withdrawal and water consumption. Now, withdrawal is the total amount of water or total volume of water extracted from a particular water body um, to support human demands. So, with proper treatments, water withdrawal for human use can be mitigated, can be reused or recycled as long as water does not get heavily contaminated. Um, Meaning, like, whenever water is withdrawn, you don't have to always do that from existing surface water bodies. Like if there's water that has been already used for something, you can treat that particular water, um, remove the pollutants, remove the contaminants, and use it again for different types of human requirements. Think about what a wastewater treatment plant can do. You don't. The point of the wastewater treatment plant is through different stages with the use of filtering techniques and biological techniques and microbial techniques. It helps you to remove suspended um, or dissolved pollutants, suspended or dissolved solids, right? And then of course nutrients can also be removed with respect to biological treatments using vegetation or microbial activities. Now, consumptive loss or consumptive loss of water refers to the loss of water due to evaporation or absorption or due to contamination. Now, the reason for these kind of consumptive loss is poor wastewater management, poor water management in general, where you actually have water flowing in open conduits rather than in closed conduits. If conduits are not properly managed, you will actually have leaching happening in the conduit, and then poor industrial management, right? Certain industrial practices may directly discharge wastewater into open water bodies for the purpose of dilution. Well, that's another way consumptive losses takes place. And then adverse environmental policies or poor environmental reinforcement is another reason. There could be laws regarding proper management of water, proper distribution of water for irrigation and for consumption, proper management regulation. Industrial regulations could be there that minimizes discharging wastewater. But what if those policies are not properly enforced? What if the policies are laxed under different while you are prioritizing economical growth and development? Then, of course, again, it also enhances the consumptive loss. Um, it's harder to mitigate for consumptive loss. Withdrawal, yes, it's you can kind of create new regulations and rules and new practices to minimize withdrawal, but whatever you lost through evaporation or pollution or absorption, that's very hard to recuperate for. That loss is sort of irreversible, um, and it takes a lot more effort to convert that loss into reusable or recyclable level. For example, look at heavy metal contamination, right, or any other degree of heavy contamination with pesticides. um, Sometimes it's harder to remove certain contaminants, right? Nitrates, phosphates, yes, you can remove them through biological means. Through allowing sedimentation or filtration, you can remove suspended solids, right? But heavy metals, you cannot remove them easily. It's harder to remove them. Pesticides or other organic pollutants are hard to be removed from contamination. Evaporative loss, you cannot recover it back, because whatever evaporated goes into the atmosphere and into the disappear into clouds or whatever. So it's harder to manage withdrawal based loss, but consumptive based losses will very hard or way too expensive to be managed unless the infrastructure itself is renovated to minimize and cut them off. So, to talk a little bit more about withdrawal and consumption based water loss, right? We are aware of what is responsible for water loss. Crop farming, livestock, particularly cattle industry, requires a lot of water. um, and for machinery cooling, it takes a lot of water, and then a lot of public based demand. And most of the processed food that is available in the market that is easy to consume is that have a high demand from the consumer, like chocolate or any sort of processed bread and cereal or other type of products. This highly processed, highly modified food is also extremely high in terms of its water footprint, right? And those things actually increases um, the water withdrawal. And then in terms of the consumptive based loss, right, poorly managed irrigation system that feeds into crop farms, right, particularly open water conduits, open water canals, will increase evaporative water loss. Sprinkler based irrigation system will tends to have a very high degree of evaporative loss, or because it actually creates this emulsification of water, and those tiny water droplets can actually easily be carried away with the wind, or like get into the atmosphere rather than getting onto the land into the crop. So that's a greater water loss in sprinkler irrigation that rather than actually supplying it to the soil or to the plants. Then flooding crop fields, so flood based irrigation, where you have like canals or furrows and you flood through these canals, or flooding entire fields like in the paddy fields, is also increasing the water loss through evaporation, because in irrigation systems like sprinklers or flooding, you provide more water than required, so whatever excess gets undergo evapotranspiration or evapotranspirative water loss. Now let's talk about depletion of groundwater. Aquifers at global scale provide drinking water for about 50%, half of the global population. Um, well, aside from some deep confined aquifers, particularly those unconfined aquifers can be reasonably considered as a renewable source of water. But contamination of any kind of an aquifer makes it non-renewable. And as I mentioned earlier, precipitation is the only source of renewing used, depleted or partly used aquifers. Now, the levels of water in those aquifers all across the world are falling gradually as a result of um, pumping or exceeding the water pumping or water extraction with compared to the lower rate of recharge. And in countries like China, India, United States, Mexico, particularly areas that global regions in the world that is responsible for grain production, and areas that are naturally occurring in desert-like habitats like Saudi Arabia, Iran, Yemen, Israel, and Pakistan are already overpumping their groundwaters, where the extraction for different purposes way exceeds recharge. So, what is the problem with over withdrawal of groundwater? What happens if you do so? Well, the sand and rock layers overlying aquifers will start collapsing into the empty aquifer, right? So that leads into collapsing ground into the aquifer. That's where you get this land subsidence, right? If you heard about the sinkhole problem, that particularly known in certain parts of the country, like in Florida, the reason is depletion of groundwater aquifers. When you lose groundwater, it kind of destabilizes the ground and creates this empty vacuums, and that results collapsing of the surface of the earth. Um, and it also results in landslides too in mountain areas or in very steep slopes. So what happens if the ground collapses? Well, then the recharge is impossible because there is no space. When an aquifer collapses, it compresses the space, so there is no place for infiltrating groundwater to recharge into. So lots of have suffered collapsing cannot recuperate. And in fact, this massive levels of surface changes in land cover conditions, loss of natural vegetation and development happening with urbanization and infrastructure development is also responsible to increase the probability of ground collapse upon aquifer depletion. Because if there is some surface cover, some natural land cover, that will prevent or slow down depleted groundwater collapse. But if you develop on the top, it further destabilizes the earth and leading to increased probability of aquifer collapse. So this could also damage infrastructure, right? I mean, sinkholes can appear in the middle of a highway, right? It could damage roadways, highways. It could also damage buildings, could lead to damage to sewer systems, water supply systems. It could completely shatter building foundations because when the ground collapses, everything built on it or underneath it can also get damaged. In coastal areas, if the aquifers collapse, the aquifers are depleted, not collapse. In the coastal areas, when the aquifers are depleted, salt water can intrude and fill in the aquifer space. And if that happens, well, even when the surface water recharges groundwater, it will not completely flush away the salinity. The salinity could be a permanent problem if coastal aquifers become infiltrated with rising sea level. So this saltwater contamination in groundwater is already a problem in certain parts of California, Texas, Florida, Georgia, South Carolina, New Jersey, and internationally in Turkey, Thailand, and Philippines. So this has already started to become a problem. So the only way to treat those areas is actually build some sort of a barrier between the coastal areas and the ocean, right? Like they're trying to do in New York, and then pump the entire groundwater out desalinate it and put it back, right? So I mean that is possible. There's technology for all of this, but it will not be cheap. Managing that kind of an infrastructure is also not going to be cheap. And with sea level rise happening in response to climate change, these kind of problems are only going to get severe, as you might increasingly lose certain coastal areas to rising sea level. So these kind of problems with groundwater depletion is extremely severe in mid parts of Middle East or Southwestern Asia. So with the development in the agro industry and with the advent of different engineering technologies since 1980s up to now, wealthy nations in Middle East like Saudi Arabia, Emirates have tapped into groundwater reservoirs, right, and used that groundwater reservoirs underlying the desert sand and growing crops in the desert. In the images to the left, you see these Arabian desert environments. To the right, you see crop fields. If you look at the crop fields, you can see they are very well organized, right? That's because those are actually, like very well created, manicured crop fields. So what they do is they drill sedimentary through the sedimentary rock sandstone kilometers and kilometers down beneath the desert sand, right, and tap into those deep underlying groundwater reservoirs. Those groundwater reservoirs, those aquifers, were geologically formed at least during the last ice age or before, right? Um, in the time when the Middle East, the modern day Middle East and Southwestern Asia sustained more temperate climate, um, that goes way beyond like 20,000 years and before that, right? So those aquifers were recharged and filled with water during ice age and before for not just centuries, like tens and thousands of years before, right? Now those are buried beneath multiple layers of sand, desert sand, right, and limestone formation. So unless you actually tap them, those reservoirs will last forever. Now, the question is, well, are those completely confined aquifers? No, because limestone, sandstones, and sandy layers are actually completely pervious, right? They are not impervious to water. Water can infiltrate through. The rainfall received in these areas are very low, between 100 to 200 millimeters per year, right? So the recharging happens very, very slowly, but extraction of those waters of this groundwaters for irrigation purposes today is extremely high, way higher than the rate of recharge, right? Despite the extensiveness of those groundwater systems, right, given the rate of recharge, they will soon disappear, and soon those countries will have to abandon these farmlands or pump water from desalination plants into these areas in order to keep those crop farms going on. The problem is not just that, like, I mean, the groundwater beneath the desert sand has been used for human consumption. Now that's not an option anymore. That's why they are also resorting to desalination to supply drinking water as well. So let me talk to you about some groundwater usage situations in the United States. Ogalla Aquifer is actually one of the largest aquifers that are currently known to occur in the United States, maybe in the world. Um, it The aquifer underlies 8 Midwestern states that are known for heavy production of staple foods, particularly corn. Um, and if you look at the ecoregion wise, it's located within the Great Plains area. Um, so one third of the US groundwater usage comes from Ogalla Aquifer. Um, and the withdrawal can be dates back to 1960s. It's known to have a very slow recharge, particularly given the precipitation is very seasonal in this part of the Great Plains. And with the increased pumping, which is about 10 to 40 times faster than the recharge rate, the groundwater table, right, or the surface saturation of soil is gradually declining. A major reason for Ogalla aquifers depletion is the government subsidy that was meant to increase farming, support farming in the Midwestern states, in the Great Plains states, right? So that's a biodiversity problem here. Naturally, Ogalla Aquifer had multiple springs, right, that actually discharges to the surface and creates surface streams. That is an important part of the native wildlife in this area. Now, these springs are drying, that actually threatened many forms of wildlife and biodiversity in the Great Plains, in the southern Great Plains of the United States. And if you want to get an idea about how extensive this is, the northernmost part of the Ogalla Aquifer occurs as north as Wyoming and Nebraska, and could even go all the way up to the southern South Dakota. The southmost distribution goes as far as Texas, right, and New Mexico, right. From east to west, it spreads from Colorado to eastern Kansas. So it's a pretty extensive system that you are looking at here with Ogalla Aquifer. So the let me talk a little bit more examples about what happens with the aquifer depletion, right? So in this image you are looking at on top right, you're looking at how groundwater has been extracted by wells, right? And then there are a few recharge points, but many anthropogenically created um, extraction wells, right? So as you can see, um, seawater can easily intrude and fill in these empty spaces created with depletion of groundwater. And in terms of the actual height, right, seawater is not that far away from the surface water table, right? So infiltration is a matter of the barrier between sea and the land. It's not a matter of the relative height of these two, right? They are like kind of head to head in terms of the heights. And that image on the leftmost corner of the slide, we are looking at, how far this electricity pole, has subsided, right? So look at the 1950 label. That's how tall. That's kind of the ground level in 1925, right over here, right? So this, I forgot to mention, we are looking at Hawking Valley of California, where you have massive level of land subsidence due to groundwater depletion. So 1925, the actual Earth level was this level, right? To that level. 1955, that level. 1977, right, is actually when this photograph was taken. So that's how the Earth has subsided in San Joaquin Valley between 1925 to 1977, right? So about half of the San Joaquin Valley has suffered some level of land subsidence, which is actually at least equal to or greater than a third of land level being third of a third of a meter of the land has subsided, has kind of sank towards the earth. That's again that's a better picture of the Ogalla aquifer with respect to its distribution across different states. And the deeper the blue color, deeper the depth of the aquifer, right? So this land subsidence is not just limited to California. It's been reported in Texas, Louisiana, Florida, and Arizona. Now that's a sinkhole that's from China that has resulted in because of collapsing earth into emptied groundwater. And then this land subsidence can actually damage buildings. If you look at this picture from Mexico City, Mexico, right, the height of the buildings are not the same, but during the stage of construction, all the buildings were constructed at the same time to the same height. But now you can clearly see certain buildings are much more shorter than the others. The reason is those sections of the building has collapsed, right? Those buildings are gradually sinking, right? I mean, over the time, what are the odds? The first floor will become the basement in those buildings, right? So they have to actually kind of re-engineer how to access those buildings. Now that's happening largely in the Mexico City, again due to groundwater depletion, because Mexico City is constructed in a desert area, right? And it's a growing city, right? And the population is increasing, so the water demand is high, and that demanding water is satisfied by pumping groundwater. So again, a pair share moment for you guys, kind of to revisit what I have explained, do some research on your own and tackle these questions. And feel free to get back to me with the questions I'm posing in any of these pair share moments.